Hello, this will be a demonstration of proposition 4 from book 6 of Euclid's Elements, which says that in equiangular triangles, the sides about the equal angles are proportional. This is going to be one of 4 similarity theorems within book 6. What we're given then is the triangle ABC. Like that. ABC. And we're going to have a similar triangle DCE. Like that. And these two triangles here are going to be placed in a straight line, so that BC is in a straight line with CE, such that the points A and D are on the same side of BC of the straight line BCE. So we're not going to have like A up here and D down here. They're going to be on the same side of the straight line BCE. And furthermore, we're given that these two triangles are equiangular, which means that ABC, which means that the angle ABC is equal to the angle DCE, and the angle BAC is equal to the angle CDE, and finally that the angle ACB is equal to the angle DEC. Okay. Now, given this, what we're going to prove is that the sides about equal angles are proportional. And what that's going to mean is that we're going to prove that AB is to BC, just as DC is to CE. Next, that BC is to CA, just as CE is to ED. And finally, that BA is to AC, just as CD is to DE. Now, the first thing that we're going to make is we're going to make a parallelogram. How we're going to make this parallelogram is like this. We know that the angle ABC is plus the angle ACB is going to be less than 2 right angles. They are two angles within the same triangle, which means by proposition 117, if you add any two angles of a triangle together, they're going to be less than 2 right angles. So the angle ABC plus the angle ACB is going to be less than 2 right angles. And we were given that the angle ACB is equal to the angle DEC, which means also by a property of magnitudes that angle ABC plus angle DEC is also going to be less than 2 right angles. Now, knowing that the angle ABC plus the angle DEC is less than 2 right angles, we have 2 straight lines upon which a third falls, such that co-interior angles are less than 2 right angles, which means that by the 5th postulate, if we produce these straight lines BA and ED far enough out, they're going to have a common point. So we're going to do that. We're going to do that by postulate 2, obviously, and produce these straight lines BA and ED to the point F, like so. Now, because the angle DCE is equal to the angle ABC, we have corresponding angles which are equal, which means by proposition 128, the 2 straight lines BF and CD are going to be parallel, like that. And of course, that also means that AF is parallel to CD. And likewise, because ACB is equal to angle DEC, we were given that, it means that AC is also parallel to FE, which means that AC is parallel to FD, which means that this whole quadrilateral, FACD, is a parallelogram. And being a parallelogram, we know by proposition 134 that the opposite sides are going to be equal to each other. So we can say that AF is equal to CD, and also FD is equal to AC. Okay. Now, within the triangle FBE, we have the straight line AC falling within it. And not only does AC fall within the triangle FBE, it is parallel to the base FE, which means by proposition 6.2, AC is going to cut the 2 sides of the triangle FB and EB proportionally, so that BA is to AF, just as BC is to CE. And we had shown earlier that AF is equal to CD, right, because they're opposite sides of a parallelogram, they're going to be equal, which means we can actually substitute it in with this proportion and say instead that BA is to CD, just as BC is to CE, which means then by proposition 5.6, we can alternate this proportion and say that BA is to BC, just as CD is to CE. Now again, we have the straight line CD falling within the triangle FBE. And CD not only falls within the triangle FBE, it is parallel to the base FB, which means it's going to cut the two sides FE and EB proportionally, so that, so that BC is to CE, just as ED is to DF. But again, we had shown that DF is equal to CA, which means that BC is to CE, just as ED is also to CA, which means again we can alternate this proportion by proposition 516 and say that BC is to CA just as CE is to ED. Yeah. BC is to CE just as BC is to CA just as CE is to ED. Now finally, because AB is to BC, just as DC is to CE, we had shown that in step 5, and also that BC is to CA, just as CE is to ED, we had shown that in the previous step 6, we can use proposition 522, that if you have any number of magnitudes and another set of magnitudes equal in number, and if you take which taken 2 and 2 together are proportional, then xi quality, the magnitudes will be proportional. So here we have that AB is to BC, just as DC is to CE, and also that BC is to CA, just as CE is to ED. So we're going to knock out the middleman BC to take the ratio BA to AC, and likewise we're going to knock out the middleman CE to have the ratio DC to ED. And having done that, we can say by proposition 522 that BA is to AC, just as CD is to DE. Now we have shown all of that which we set out to prove. We wanted to prove that AB is to BC, just as DC is to CE, which we had shown in step 5, and that BC is to CA, just as CE is to ED, which we have shown in step 6, and finally that BA is to AC, just as CD is to DE, which we have shown in the final step 7, which means we are done with the proposition, therefore, etc. Q, E, D. Again, this is going to be one of your similarity theorems within book 6. There are 4 of them. There's this one and then the next 3 props. Just like the congruency theorems within book 1, we commonly abbreviate these based on the equal characteristics. So this is going to be your angle similarity theorem, right? Because we were given that the 2 triangles are equiangular. So the 3 angles are going to be equal. But we can actually shorten this to just angle similarity. Because if we know that within 2 triangles, 2 angles be equal to 2 angles. So like for example, if we know that ABC is equal to DCE and that BAC is equal to CDE, then it must be the case that angle ACB is equal to the angle DEC, right? Because we know that the 3 angles of any triangle have to add up to 2 right angles, which means that the sum of the interior angles of the triangle ABC is equal to the sum of the interior angles of the triangle DCE. And if we have 2 of the angles equal to 2 of the angles, then by common notion 3, if we subtract those 2 equal angles from both sides, then the remaining angle is going to be equal. So what that's going to mean is that, like for example, ABC plus BAC plus ACB is going to be equal to angle DCE plus CDE plus DEC, right? Because we know they both have to add up to 2 right angles by proposition 132. And they add up to the same thing, which means they're equal to each other by common notion 1. And we know that 2 of these angles are equal to 2 of these angles. So we know that, like, for example, ABC is equal to DCE. So by common notion 3, we can subtract that from both sides and say that the angle BAC plus the angle ACB is equal to the angle CDE plus the angle DEC. But again, if we know that the angle BAC is equal to the angle CDE, we can subtract that again and say that the angle ACB is equal to the angle DEC. And that is how we know that if we know that within 2 triangles, 2 angles be equal to 2 angles, then the third angle is going to be equal to the third angle. And it's because of that that this similarity theorem is often not called angle similarity theorem, but just double A, angle similarity. Other than that, I've got nothing to say about this proposition, so I'll end the video here and move on to 6.5.